Hi, so today we're going to discuss the spectrum of electromagnetic waves, the polarization of light waves, reflection, refraction, dispersion and prisms, Huygens principle, and total internal reflection. So we will now discuss the spectrum of electromagnetic waves. So electromagnetic waves are produced by accelerating charges and they travel in vacuum with a speed c, wavelength lambda, and frequency f, okay? And there are different types of electromagnetic waves, all differing in frequency and wavelength, as you can see here, from low frequency to high frequency. So first we have radio waves. So radio waves are generated by accelerating charges, for example, in a radio antenna and LC oscillators, and they are used in radio and television systems, okay? And then we have microwaves with wavelengths ranging from 1 millimeter to 30 centimeters, and they are used in navigation systems, microwave ovens, and in studying the atomic and molecular properties of matter due to their short wavelengths, okay? And then we have infrared waves, which have wavelengths ranging from 1 millimeter to 7 times 10 to the minus 7 meter, and which is the longest wavelength of visible light, and are produced by objects at room temperature. And infrared are used in vibrational spectroscopy and infrared photography, okay? Then comes visible light, which is the part of the spectrum that is visible to us humans and which we can detect, right? And light is produced by hot objects and by electrons in atoms and molecules. And the wavelength of visible light range from 4 times 10 to the minus 7 meter for violet to red, which is 7 times 10 to the minus 7 meter. And then comes ultraviolet light, which has wavelength ranging from 4 times 10 to the minus 7 meter, which is 400 nanometer, to about 6 times 10 to the minus 10 meter, which is 0.6 nanometer, okay? And the sun is a main source of UV light and can cause sunburns. Then we have X-rays with wavelengths ranging from 10 to the minus 8 meter, which is 10 nanometer, to 10 to the minus 13 meter, or 10 to the minus, which is 10 to the minus 4 nanometer, okay? And can be produced, so X-rays can be produced by high energy electrons bombarding a metal target, as we will see in other videos. And they are used in medicine and also in the study of crystals. And this is because of their short wavelengths, which is comparable to the distances of atomic separation in solids. And that distance is about 0.1 nanometer, okay? And because of their high energy, they can damage living tissues if there is an overexposure to X. So then we have gamma rays with wavelengths ranging from 10 to the minus 10 meter to less than 10 to the minus 14 meter. And gamma rays are emitted by radioactive nuclei and also in certain nuclear reactions. And because of their very high energy, they are highly penetrating and can produce serious damage in living tissues. And this is why people working near such radiations are protected with layers of heavily absorbing materials such as lead, okay? So we will now discuss the polarization of light waves. So as we have seen in video 6 of electromagnetism, the electric and magnetic vectors associated with an electromagnetic waves are perpendicular to each other, right? And to the direction of the wave propagation. So the direction of polarization of an electromagnetic wave is defined to be in the direction at which E is vibrating, okay? So let's consider a beam of light emitted by atoms in a light source. So in that case, the beam consists of a large number of waves, where each atom produces a wave with a specific orientation of the electric field that corresponds to the direction of vibration in the atom, right? And since all directions of vibrations are possible, in the group of atoms in the light source, it follows that the beam emitted is a superposition of the waves produced by the individual atoms and is therefore unpolarized, as you can see here. Okay? So the direction of propagation here is taken perpendicular to the page, represented by the dot here. Okay? And as you can see, the time-varying electric field vector lying in a plane perpendicular to the direction of propagation can be in any direction with equal probability. So a beam of light is said to be linearly polarized if the orientation of the electric field vector E for all individual waves is the same at all times at a certain point. So all waves will have the same orientation of E. And this kind of wave is also known as a plane polarized wave, where the plane formed by E and the direction of propagation is known as the plane of polarization of the wave, right? So this is an example of a plane polarized wave. So as you can see, this is a linearly polarized or plane polarized wave along the y direction, and the plane of polarization is the xy plane. So as you can see, E is vibrating in the y direction, and the wave is propagating in the x direction. A linearly polarized wave like this can be obtained from an unpolarized wave, as in this setting here, by removing from the unpolarized wave all of the electric field vector components except one that lies in a certain single plane. That is parallel to a characteristic direction known as the polarization direction. Okay? And this can be done using a material known as the Polaroid, like this one. So in such a material, the molecules have selective absorption, where they absorb light whose electric field vector is parallel to their length, and transmit light whose electric field vector is perpendicular to their length. Okay? And this direction, which is perpendicular to the molecule length, is referred to as the transmission axis. So this is the transmission axis perpendicular to the molecule length. So a polarizer passes the components of the electric field vectors that are parallel to the transmission axis, while electric field components perpendicular to the transmission axis are absorbed. So we will now find an expression for the intensity of the transmitted polarized light known as Malice's law. So as you can see here, an unpolarized light beam is first incident on a polarizing sheet known as the polarizer. Okay? So this is the polarizer, and the polarizer polarizes the incident light along its transmission axis. Okay? And the transmitted electric field vector is E naught. Then the beam passes through a second polarizing sheet known as the analyzer, which has a transmission axis that is at an angle of theta to the axis of the polarizer. Okay? And so the component of E that is perpendicular to the transmission axis of the analyzer is completely absorbed, while the component that is parallel to the axis of the analyzer pass, and it is E naught cosine theta. So this equation, the intensity is equal to E max square over 2 mu naught C, that we discussed in video 6 of electromagnetism, shows that the intensity varies as the square of the amplitude of the electric field. And so the transmitted intensity varies as the square of the transmitted amplitude, which is, so it's E naught square cosine square theta over 2 mu naught C. And the first term, so E naught square over 2 mu naught C, is the intensity of the polarized wave incident on the analyzer. So it is, we can write it as I max. And so the intensity of the transmitted wave from the analyzer is I max cosine square theta. okay? So this expression applies to any two polarizing materials whose transmission axes are at an angle theta to each other. And so the transmitted intensity from the analyzer is maximum when the two transmission axes are parallel, so when theta is equal to 0 or 180 degrees, and it is the transmitted intensity is 0 when the transmission axes are perpendicular to each other. So we have so far discussed the wave nature of electromagnetic radiation, and we have showed that visible light is electromagnetic waves of a certain frequency, right? And we will show in later videos that the electromagnetic wave model of light could not explain some experiments, such as the photoelectric effect, in which electrons are ejected from a metal when the surface of that metal is exposed to light, okay? So this led to the conclusion that light has a dual nature. So in some cases, light acts as a wave, and in other cases, it acts as a particle. But here in this video, and also in the next video of discussing light, we will only focus on light properties that can be explained using the wave model. So here we will discuss the behavior of visible light at an interface between two media, and such behavior can then be applied to all electromagnetic radiation. And so we will discuss the laws of reflection and refraction, and this can be done using a simplification model known as the ray model, okay, or the ray approximation. So in this model, a ray of light is a straight line along the direction of propagation of the wave. So a ray of light represents the path of the wave as it travels, okay? So this is the direction of the wave propagation. These are rays of light. And so studying optics involve geometry based on the straight lines of the rays, right? And so in this ray approximation, all phenomena explained by the ray approximation, it does not depend on fully incorporating the wave nature of light, other than using the fact that the propagation of the wave is along a straight line, okay? So a set of light waves are represented by wavefronts, okay? And for a plane wave, in which we discussed in the electromagnetic video 6, the wavefront is perpendicular to the direction of propagation of the wave, okay? So the wavefront is perpendicular to the ray, because the ray is in the direction of propagation of the wave, right? At every location in space. So this is the ray model, okay? And we will now discuss the limit at which this ray approximation can be applied. So let's suppose that a plane wave passes through an opening of size d, okay? And suppose that d is large relative to the wavelength, okay? So in this case, as you can see, the individual waves emerging from the opening will continue to move in a straight line, right? And note here also that we can neglect some small edge effects. And so in this case, the ray approximation is valid, okay? But if the size of the opening gets smaller and is of the order of the wavelength, as you can see here, then the waves and the corresponding rays will spread out from the opening, right? In all directions. And this is known as diffraction. And we say that the incoming plane wave undergoes diffraction as it passes through the opening, okay? And now let's suppose that the opening is small relative to the wavelength. Then the diffraction is stronger, okay? And as you can see, in this case, the opening can be approximated as a point source of waves, right? And so diffraction becomes more pronounced as the ratio d over lambda, so d over lambda approaches 0. And so the ray approximation assumes that lambda is much less than d. so that we can neglect diffraction effects, right? Because diffraction effects needs the full wave model of light to be explained, right? So we will show in the following that the ray approximation is very good in studying mirrors, lenses, prisms, and other optical instruments such as telescopes and cameras. So we will now discuss reflection. So consider rays of light incident on a surface. So if the surface is not perfectly absorbing, then some of the light is reflected, right? And in the case of a very smooth surface, the reflected light rays are parallel, okay? And the reflection here is known as specular reflection. But if the reflecting surface is rough, then the rays are reflected in different directions, and this is known as diffuse reflection, okay? A note here that a surface is considered smooth if the surface variations are small compared to the wavelength of the incident light, okay? So let's consider a light ray traveling in air and incident at an angle of θ1 to the normal of a smooth surface, okay? So experiments show that the incident ray, the reflected ray, and the normal to the surface all lie in the same plane. And also it shows that the angle of reflection is equal to the angle of incidence. So θ1 is equal to θ1 dash, and this is the law of reflection. So for a rough surface and diffuse reflection, the law of reflection applies with respect to the local normal, okay, which varies from one location to another on a rough surface, okay? So in this video, we will only consider specular reflection, like this one, okay? Also note here that the path of a light ray is reversible, which means that if the ray is originated here, it will follow the same path in reverse and reach the same point here. And this reversible property is useful when solving problems. So let's consider now an example of two mirrors making an angle of 120 degrees with each other. So this is the first mirror, this is the second. So if a ray is incident on the first mirror at an angle of 70 degrees to the normal, then we want to find the direction of the ray reflected from the second mirror. So we want to find θ dash, okay? So first we find the angle that the reflected ray from the first mirror makes with the horizontal. So it's delta. So delta is equal to 90 minus 70 is equal to 20 degrees. Then we know that the sum of a triangle angles is equal to 180. So this is the triangle. So gamma is equal to 180 minus 120 minus 20 is equal to 40 degrees. And this gamma is the angle that the ray reflected from the first mirror makes with the second mirror, okay? So from this we can find theta, which is 90 minus 40 equal to 50, and from the law of reflection, the angle of the second reflected ray, θ dash, is also equal to 50 degrees. So we will now discuss refraction. So suppose a ray of light is traveling in a transparent medium and is obliquely incident on a boundary to another transparent medium, okay? So part of the ray is reflected and the remaining part is transmitted into the other medium, but this transmitted ray experiences a change in direction at the boundary and is said to be refracted, okay? So this is the incident ray. When it is transmitted, the light changes direction, and this is known as refraction. So experiments show that the incident ray, the reflected ray, and the refracted ray all lie in the same plane, okay? And also that the angle of refraction, θ2, depends on the properties of the two media and on the angle of incidence, through the relationship sine theta 2 over sine theta 1 is equal to v2 over v1. So v1 is the speed of light in medium 1 and v2 is the speed of light in medium 2, okay? And as in the case of reflection, the path of a refracted light ray is reversible. So suppose the ray is originated here, then it will follow the same path in reverse and reach this point here, okay? But note here that in this reverse situation, the reflected ray would be in the glass, okay? So this equation shows that when light moves from a medium in which its speed is high to a medium in which its speed is low, then theta 2, the angle of refraction, is less than theta 1, which is the angle of incidence, okay? So in this case, for light traveling from air to glass where the speed is high to where the speed is lower, theta 2 is less than theta 1 and the refracted ray is closer to the normal, right? But if the ray moves from a medium where it travels relatively slowly, like in glass, to one where it travels faster, like air, then theta 2, the angle of refraction, is greater than the angle of incidence, and the refracted ray deviates away from the normal, okay? So in air, light has a speed of c equal to 3 times 10 to the power 8 meter per second, while in glass, the speed of light is approximately 2 times 10 to the power 8 meter per second, okay? And the reason why light slows down in glass is the absorption and re-emission of light by the atoms of the glass as it propagates, okay? So the details of this process can be best explained by quantum physics, or also using the classical oscillator model of the atom, where the atoms are considered as oscillating dipoles. And this, we will discuss this in another video, okay? But the result is that the average speed of light in the glass is lower than c. So as the light here emerges to the air, its average speed is back to c, okay? So next we will show a derivation of Snell's law of refraction. So we know that light passing from one medium to another is refracted because the average speed of the light is different in the two media, okay? So light travels fastest in vacuum with a speed c equal to 3 times 10 to the power 8 meter per second. So the index of refraction n of a medium is defined as c over v, okay? And v is the speed of light in the medium, and this is c, the speed of light in vacuum. So the index of refraction is a dimensionless quantity because it's the ratio between two speeds, okay? So n is greater than or equal to unity because v is less than or equal to c, right? So for vacuum, n is equal to 1, and for glass, n is approximately 1.5. So one thing to note here is that as the wave travels from one medium to the other, its frequency does not change, okay? So its frequency remains constant. So this figure here shows how the wavelength of light changes as it passes from one medium to the other. But because the velocity of light also changes, so as you can see, the velocity is also lessened here, the frequency, which is the ratio of the speed to the wavelength, does not change. Because if it does change, then the wavefronts would pile up here at the boundary, and this does not occur. So the frequency must be constant as the light ray passes from one medium to the other. So we have F1 is equal to F2 is equal to F, and V1 is equal to lambda 1F, and V2 is equal to lambda 2F. So because V1 is not equal to V2, it follows that lambda 1 is not equal to lambda 2. And if we divide lambda 1 over lambda 2, we get V1 over V2 equal to C over N1 over C over N2, and is equal to N2 over N1. And this gives this expression. So the index of refraction of any medium is given by n is equal to lambda over lambda n, where lambda is the wavelength in vacuum and lambda n is the wavelength in the medium. So we have, using the previous equation here, n1 sine theta 1 is equal to n2 sine theta 2, okay? And this expression was experimentally discovered by Snell and is known as Snell's law of refraction. And note that other waves, such as sound waves or seismic waves, also experience refraction. And so Snell's law is a model for a wave under refraction, okay? So we will now discuss dispersion and prisms. So in the preceding section, we defined the index of refraction of a material, n equal to c over v, where c is the speed of light in vacuum and v is the speed of light in the material, okay? And we said that for glass, it's approximately equal to 1.5. But experiments show that the index of refraction depends on the wavelength of the light, okay, and that this results from the dependence of the wave speed v on the wavelength. And this is known as dispersion. So the figure here shows how the index of refraction of glass varies with wavelength, okay? And so because n varies with lambda, it follows from Snell's law that the angle of refraction also depends on the wavelength of the light, right? And as you can see, the index of refraction generally decreases with increasing wavelength in the visible range. And so violet light of wavelength of about 400 nanometer is refracted more than red light of wavelength of about 650 nanometer, okay, when a ray passes from air to a material. So because of this dispersion, when a beam of white light, which is a combination of all visible wavelengths, is incident on a prism of glass, the different wavelengths or colors refract through different angles, okay? Because n is slightly different for each wavelength. And so the rays emerging from the second face of the prism are separated into the visible spectrum, as you can see in this figure. And so violet light is refracted the most, and then less and less for the remaining colors, and red light is deviated or refracted the least. So we will now discuss Huygens' principle. So in 1678, Huygens proposed a geometric model that allows one to determine the position of a wavefront from an earlier wavefront. So Huygens assumed that light consists of waves rather than particles, and he had no knowledge of the electromagnetic nature of light, but he proposed this geometric construction method to understand many aspects of light propagation. So Huygens' principle states that all points on a given wavefront are taken as point sources that produce secondary spherical waves called wavelets, okay? And those wavelets propagate outwards with speeds that are characteristics of waves in the material. So from Huygens' principle, after some time interval has passed, the new wavefront is the surface that is tangent to the wavelets. So to understand this, let's consider this figure here, which shows Huygens' construction for the case of propagation of a plane wave and for the case of propagation of a spherical wave, okay? So for this first case of a plane wave moving in free space, at t equal to 0, the wavefront is a dash, okay? And each point on this wavefront here is a point source of a wavelet, okay, according to Huygens' principle. So let's consider 3 points on this wavefront. So each point is radiating a spherical wave indicated by these arcs here. Okay, so each arc has a radius of c delta t, where c is the speed of light in free space and delta t is the time interval during which the wave propagates. So according to Huygens' principle, the new position of the wavefront is the surface that is tangent to the wavelets. So the surface that is tangent is BB dash, and it is parallel to A dash, right? So this plane BB dash represents the wavefront at the end of the time interval delta t. Okay, so as you can see, the plane wave propagates, and after this time interval, the wavefront is still a plane. Okay, it's still a straight line like that. So this is how the plane wave is propagating. And in a similar way, this figure here shows Huygens' principle applied for an outgoing spherical wave. So the line tangent to the wavelets form another wavefront, a spherical wavefront, okay? So, and Huygens' principle can be demonstrated in a shallow tank of water, as you can see here. So plane waves are produced here to the left, and in the plane wave, okay, each point on the wavefront acts as a source of circular waves on the two-dimensional water surface, okay? So at a later time, the wavefront, as you can see here, is still a plane, a straight line forming a plane wave. And as this plane wave, so this is a propagating plane wave, it then encounters a barrier with two small openings. Then all wavelets except those at the two small openings are reflected back. So if the openings are very small, the situation can be modeled as if only one source of Huygens wavelets exists at each of the two openings, okay? And so the wavelets from these two openings emerge as two-dimensional circular waves propagating outwards. So this is an example of diffraction, and we will discuss this in the next video. And also you can see that the two sources of circular waves, so they interfere with each other, and also we will discuss interference in the next video. So we will now derive the laws of reflection and refraction using Huygens' principle. So for the law of reflection, you can see that for the incident light rays here, the incident light, the line AB is the plane wavefront, right? Because the rays are perpendicular to the wavefronts. This is a plane wave incident on the surface. These are the wavefronts perpendicular to the rays, right? So just as ray 1 strikes the surface here at A, the point A is a source of a spherical wave, and it will emit a Huygens wavelet. So it will be sent out from A, and this is a picture at a later time, delta t. So this wavelet arrives here, passing through D. And so you see that the reflected light makes an angle of gamma dash to the surface. And at the same time A emits a wavelet, the point B also emits a Huygens wavelet, right? Because as we said from Huygens' principle, each point on the wavefront is a source of a wavelet. So it will emit, B will emit a Huygens wavelet, and at a later time of delta t, it will arrive here, passing through C, right? So this is the time. This time interval is the time it takes the second ray to strike the surface. So at that time, the wavelet from A has arrived here, and the wavelet from B has arrived here, passing through C. And so the incident light is making an angle gamma to the surface. So because both ray 1 and 2 move with the same speed, we have AD is equal to BC is equal to C delta T. And using a geometric analysis, you can see that the two triangles ABC and ADC are congruent because they have the same hypotenuse AC. And so cosine gamma cosine gamma is equal to BC over AC. So it's BC over AC. And cosine gamma dash is equal to AD over AC. Okay? And gamma is equal to 90 degrees minus theta 1. Because here, this is the incident, this is gamma, it's equal to 90 minus theta 1, and gamma dash is equal to 90 degrees minus theta 1 dash. And because, because here BC is equal to AD, we have cosine gamma is equal to cosine gamma dash, and gamma is equal to gamma dash, and this gives theta 1 is equal to theta 1 dash, which is the law of reflection. So for Snell's law, when ray 1 strikes the surface, a Huygens wavelet is sent out at A. So it is shown here after a time interval delta t has passed. And this time interval is the time required for ray 2 to strike the surface. So at the instant A emits a Huygens wavelet, at the same instant B also sends out a Huygens wavelet. And after the time required for ray 2 to reach to strike the surface, you can see this wavelet of B reaches here, C. So this is the wavelet sent out from A, and this is the one sent out from B. And as you can see, the two wavelets travel in different media during this time interval. So the radii of the wavelets are different because the speed of light is different in the two media. So the radius of the wavelet from A, which is AD, is equal to V2 delta t, where V2 is the speed of light in the second medium, right? And the radius of the wavelet from B, which is BC, is equal to V1 delta t, where V1 is the wave speed in the first medium. So from the triangles ABC and ADC, we have sine theta 1 is equal to BC over AC, and sine theta 2 is equal to AD over AC, and we substitute for BC and AD, and then we divide the two equations, we get this expression. And then we know that V1 is equal to C over N1, the index of refraction of the first medium, and V2 is equal to C over N2. And we substitute for V1 and V2, and we get this expression, which is Snell's law of refraction. So we will now discuss total internal reflection. So total internal reflection occurs when light travels from a high refractive index medium into a lower index of refraction medium, such as from glass to air. Okay, so let's consider a light ray traveling from medium 1 to 2, where N1 is greater than N2. So as you can see, for normal incidence, all of the light is transmitted, but for oblique incidence, the light is partially refracted and partially reflected, as for this ray and this ray, right? And the refracted rays are deviated away from the normal because N1 is greater than N2, as we have seen in the previous section. But at a certain angle of incidence, known as the critical angle theta c, the refracted ray is parallel to the boundary. So this is The refracted ray here is parallel to the boundary, and the angle of refraction is 90 degrees. Okay? And if the angle of incidence is greater than theta c, as for this ray, last ray here, so the angle of incidence is greater than theta c, then the incident ray is fully reflected at the boundary and there is no refracted ray. So as you can see, it's fully reflected. So in this case, the boundary behaves as a perfectly reflecting surface for an angle of incidence greater than theta c, right? So this is known as total internal reflection, so it occurs at angles of incidence greater than the critical angle. And in this case of total internal reflection, the law of reflection applies, so the angle of incidence is equal to the angle of reflection, okay? And all of the energy of the incident light is reflected. So to find this critical angle at which total internal reflection occurs, we can use Snell's law, where theta 1 is equal to theta c, and theta 2 is equal to 90 degrees, right? This ray, this green ray here. So this is, we substitute in Snell's law, and we get sine theta c is equal to n2 over n1, and this equation applies only when n1 is greater than n2, because if n1 is less than n2, then sine theta c will be greater than 1, which is not true, because the sine of an angle is never greater than 1, right? Total internal reflection occurs only when light travels from a medium of a high index of refraction to one of a lower index of refraction. So for glass, n is equal to 1.52 and the critical angle is about 41 degrees, and for diamond the critical angle is about it's less, so it's about 24 degrees, and this what contributes to the sparkle of a diamond. So one application of total internal reflection is in fiber optics, where transparent plastic rods are used to transport light from one place to another, carrying information at an extremely high rate, okay? So as you can see in this figure, because of total internal reflection, light is confined to the rod. So if the rod is flexible and made of thin fibers, it is known as an optical fiber. And as the light bounces along the core of the optical fiber, it loses very little of its intensity as it travels. And so fiber optics have many applications, such as in telecommunication, because they can carry a greater volume of information than electrical wires. And also they are used in medicine. So I included some solved examples. Thank you for watching, and please don't forget to like and subscribe, and see you in the next video.